Hello, my name is Sam Billand, and today we're going to be talking about Lab 1 charged tapes from Physics 2212. First, the purpose of this lab is to determine and calculate the deficit of charge on a piece of positively charged U-tape, and this is done by analyzing the effect of the electric force from a similarly charged piece of U-tape. Before we could perform the actual experiment, we had to make initial observations about charged U-tapes and their interactions. First, when brought together, two pieces of charged U-tape repel each other. This means they have the same charge. This means they have the same sign of charge. Next, when the U-tape is brought near neutral objects, they attract to one another through the polarization of the neutral object. Finally, when the U-tape is brought near negatively charged plastic pen, they attract to one another. Therefore, with all of these conclusions, you can assume that the U-tape is positively charged, especially since it attracts to the negatively charged plastic pen. Next, here are some main physics principles applied and assumptions used throughout the lab. First, here are the two main equations used in the lab, that being the electric field of a point charge and the electric force of a point charge. Furthermore, here are some very key assumptions used throughout the lab. The first being that the long tape is considered to be a point charge in calculation, and that basically means that all the charge is concentrated at the center of the tape. Furthermore, both U-tapes are given the same amount of positive charge when being charged, so therefore Q1 equals Q2. Here are some of the measured values recorded during the experiment. As you can see, they are all reasonable within the scope of analyzing the effect of the electric field and its force on positively charged U-tapes. Furthermore, all the measured values have the proper units. In addition, here's a coded rendition of the experiment, taking into consideration the assumption that the long pieces of U-tape can be considered as a positively charged point charge. As depicted from the arrows, you can see that the forces on each point charge are in equilibrium with one another, and that is further shown in the print statement that gives these exact values. As a note, there is an unseen force of gravity arrow acting on tape A, the bottom point charge, because it is masked by the downward electric force arrow, since they are the same magnitude. Furthermore, there is a main connection between the principles and the model that you saw before. That connection being that the forces are in equilibrium on each charge tape, and that is represented in the model by the arrows on the point charges. Essentially, the electric field force between the tapes needs to equal the force of gravity on the tapes. This is an obvious statement because tape B, the top tape, would only float above tape A if the electric field force repelling it from tape A would equal the force of gravity on tape B. To find these values in calculation, first, you must calculate the force of gravity on one piece of tape. Then, given the assumption stated previously, you know that you can plug that value into the electric force equation and determine the deficit of charge on either piece of tape. But what if electrons had positive charge and protons had negative charge? Would anything change? No. And this is because, when charged, each piece of tape would have the same sign charge and would still repel each other. And since the charge of a proton and the charge of an electron are the same in magnitude, the distance at which they repel each other would remain the same. Thus, nothing would change in the experiment. Furthermore, why is it important to handle charged tape as little as possible? And what happens when it comes in contact with your hands? Well, it is very important to be careful when bringing tape in contact with other objects, since charge is easily transferred. And this is because any transfer of negative charge to the tape makes it more neutral, therefore reducing its electric force effect and diminishing the effects of the experiment. Specifically, when coming in contact with human skin, electrons from the salt water on our skin would transfer to the tape, making the positive tape more neutral. In conclusion, through calculation that was later confirmed through the coded model, the final deficit of charge left on one piece of tape in the experiment is 1.26 times 10 to the negative 8 coulombs. And therefore, through experimentation and calculation, it is easy to determine the deficit or excess charge on any common everyday charged object.